Welcome friends in the next session of MOOCs on computer vision. Today in this session we'll see a concept of geometric transformations. The geometric transformations are various operations which are performed on basic elements which are called as geometric primitives. The geometric primitives are nothing but simple objects like points, line, circle, square, rectangle, etc. In computer vision, there is a great significance of geometric transformations because with the help of many operations, different geometric primitives, their shape gets changed. They are either scaled down or they can be rotated or they can be translated. So in geometric transformation, three steps are important. First step is translation, second step is rotation, and third step is scaling. So either one of these operations or in combination of these multiple operations are executed on various geometric primitives, and these geometric primitives in turn are used to build the complex objects. So in computer vision, geometric primitives and geometric transformations, they are the most significant elements in order to construct a new object and in order to perform any operation on the object. So in today's session, we'll learn 2D transformations which are geometric transformation. The first is scaling, second translation, and third is rotation. So let's start with the session. So let's start with the scaling operation, scaling in 2D. The point x and y to be scaled by amount ax and ay, and after this ax and ay, which are the scaling parameters at x-axis and along y-axis, this xy point is transformed into new dimension, and that is represented by x dash and y dash. Therefore, we write equation for x dash as x dash is equal to ax into x and y dash is equal to ay into y. So original point x is multiplied by a scaling parameter ax to get the new point x dash, and original point y is multiplied by scaling parameter ay to change it to the new coordinate y dash. So x and y are converted into x dash and y dash. In matrix form, we can write this scaling operation as, say, P matrix, P dash matrix is the new matrix which is formed after scaling operation, that is equal to A matrix into P matrix, where the matrix P dash is given by x dash and y dash, matrix A is given by ax 0 and 0 ay. So matrix A is a two-dimensional matrix, and finally matrix P, which is our original location, is equal to x and y. In homogeneous coordinate system, the representation of scaling can be seen as, say, P dash is equal to A into P, where P dash matrix can be written as x dash, y dash and 1. Small a matrix is equal to ax 0 and 0, as the dimension of a matrix is now 3 by 3. So we'll append it by zeros. So 0, ay 0 and 0, 0, 1. While our original matrix P, it will remain as x, y and 1. Remember that in homogeneous coordinate system, we always append 1 in the matrix as against the Cartesian coordinate system. In computer vision, the homogeneous coordinate systems are used. Let's consider one important note, that scaling is performed about the origin 0, 0 and not about the center of line or polygon or any other object. So let us consider a scaling factor a. If a is greater than 1, then it will lead to enlargement of object, and the object will move away from origin. So wherever a value is greater than 1, 7.52, the object is enlarged, its size is increased, and the object will move away from the origin. When a value is equal to 1, then the object is not changed, so it will leave the object alone as it is. When a value is less than 1, then as against a above 1, the object will shrink. So it will shrink the object and it will move the object towards origin. So let's see one more pictorial representation of the same. Let us consider that a is less than 1. Let us draw the object. So that's my y-axis, this is my original x-axis, and when value of a is less than 1, it will shrink the object. So originally the object location is, for example, situated at these points, and when a is less than 1, then the object will change into a smaller dimension. Approximately this is drawn, and the important point is that the object has moved towards the origin. On the other hand, when a is greater than 1, then the opposite effect happens. If that's my original object, then if a is above 1, the object gets enlarged and it will move away from the origin. Let's consider second operation, second geometric transformation, which is known as translation in two-dimensional. So we have a original point at location x and y, and let dx and dy are the new values which are to be shifted, and after performing translation, this xy is changed to x dash and y dash. So equation of x dash is equal to x plus dx, while equation of y dash is equal to y plus dy. So in original point, this x is shifted by this amount dx, and it is translated to form the new value of x dash. Similarly, original point is shifted by amount dy to form a new value which is y dash. In homogeneous coordination system, let us write down the formula equation. So in homogeneous coordinate system, the translation representation is given as x dash, y dash and 1 is equal to, we have the values of matrix as 1 0 dx, 0 1 dy and 0 0 1, and here we have the original P matrix x, y and 1. So in a compact form, this is written as P dash is equal to P plus T. So if we write this x dash is equal to x, y becomes 0 and x plus dx. Similarly, we get y dash as y plus dy, and we have 1 equal to 1. Let us see a pictorial representation of this translation. We have a original point over here with values x and y, and this point gets translated by the amount dx and dy, and that's a new point x dash and y dash. So this is a translation of xy point to form the new point x dash y dash in two-dimensional form. Let us learn the third operation and the last operation of geometric transformation, which is rotation in 2D. So a point x comma y is converted into x dash and y dash, and it is rotated about the origin by angle theta. So the equation x dash new value is equal to x cos theta minus y sin theta, and y dash is equal to x sin theta plus y cos theta. Sin and cos, they are much costlier than addition or multiplication. So this rotation in 2D, this geometric transformation is having a enough computational cost as compared to scaling or simple translation. Let us consider the representation of rotation in homogeneous coordinate system. So in homogeneous coordinate system, the rotation is represented as p dash is equal to r into p. So matrix p dash is written as xy1, r matrix is written as cos theta minus sin theta and 0, sin theta cos theta and 0, and 0 0 1, while the matrix P is written as xy1. This P dash matrix is the new values x dash y dash 1, R matrix is represented by these components, and P matrix is having original location x, y and 1. So rotation is always performed about the origin. So let's have a look to pictorial representation of rotation operation. That's y axis, x axis. Assume that the object is present initially at this location. This object values, the particular point is having x and y as the location, and it has the initial angle as phi. Now the angle has to be rotated, so this object is moved to another angle around with respect to origin, and this angle of rotation is given by theta, and the points now over here, it is x dash and y dash. So x and y are changed to x dash and y dash by adding the angle of theta over here. So theta is the angle of rotation. So friends, we have seen in this session a very important concept of geometric transformations. These are simple operations like translation, scaling and rotation, which are performed on simple objects. These simple objects are nothing but geometric primitives. In computer vision, these geometric primitives are used to construct more and more complex objects. The geometric primitives can be a simple point, or it can be a simple line, or it can be any object like square, circle, rectangle, etc. So geometric transformations like scaling, translation and rotation, these are performed on these geometric primitives in order to form a new process and the new object. So that's all for this session today. Thank you. Thank you so much.